So good morning. My computer decided just to shut down, but I've managed to open it again. So good morning. I hope you are well this morning. I have just decided we start on the sulfonamides. Might have just left a little bit of the anti-leprosy drugs, but not much, so we'll summarize later. And because of time, I thought it's wise. Let's start on the bigger group, which might be our last group. And this group is we still have the lincosamides, which is also very small. So sulfonamides were some of the first antibacterial agents to be discovered. Actually, they were discovered before the penicillins. But because of when they were discovered, they were like a wonder drug, working fantastically, and therefore they were misused. There was a lot of irrational use of the sulfonamides. So there was the microorganism had resistance very quickly. As we will see, the sulfonamides are a very simple molecule, and because of their simplicity, they of course are not naturally occurring. They are totally synthesized. They have a simple molecule. They are not antibiotics as per our definition, because they are not synthesized, or they're not synthesized, or they're not produced by microorganisms. They are actually synthesized in the lab. We look at them, they have a completely different structure from the drugs that we have looked at. Their mode of action is different from also what we have looked at. So it is a new experience, because as we have said, these drugs are quite different. So again, I'll not shout a lot. I will try to move as fast as possible, because these ones are not tough drugs. So we can say they are the first compounds to be effective, and bacterial agents in safe dose ranges were quite safe. Again, they were discovered by chance. We are going to see when a certain dye was, the effects of a certain dye were being observed, it was discovered that that dye did have some antibacterial activity. Remember, we are calling them antibacterial. They are not antibiotics, because they are not produced by living organisms, but they act against, of course, living organisms to suppress or kill them. Chemically, it is a molecule called the sulfonamide or the sulfonilamide. And the sulfonamide or sulfonilamide group is this. The SA2 is usually S double bond O NH2. So these two oxygens are joined on the sulfur, which implies that that group is a very potent, as we have said, it is a potent electron withdrawer and then attached to NH2. And because it's a potent electron withdrawer, then you find that this nitrogen can be electron deficient, and one of these hydrogens can actually be an acidic proton. That we are going to see as we move on, but we only need to understand that this is a sulfonamide or sulfonamide group S double bond. This is not a very new group, because when you are looking at the non-steroidal anti-inflammatories, this sulfoamide group, it's the same group, the sulfoamide group or the sulfonilamide group or sulfonamide group attached to an aniline. That means this group is directly attached to a benzene ring, and the benzene ring is attached to an amino group. So that's what we're talking about. An aniline is a benzene group attached to an amino group, and the sulfonamide group and the amino group, all the aniline we will find they are para to each other. Structure related to para-aminobenzoic acid. Kindly draw the structure of para-aminobenzoic acid. Benzoic acid is a benzene ring with a carboxylic group, and then the para-amino for sure is at the para position. So when we look at the structure of the sulfonamides, the structure of the para-aminobenzoic acid, they are structurally similar, just as we said about dapsone and para-aminobenzoic acid. And indeed, that is where we get the selective toxicity. This group is also present in other non-antibacterial compounds. And of course, we have not included even the coxibs. Even the coxibs do have the sulfonamide group or the sulfonilamide group, and they are they do not have antibacterial activity. You also find this group in other drugs, like the sulfonylureas. The sulfonylureas are used as oral hypoglycemic agents, the benzothiazides, oral diuretics. Benzothiazides are diuretics. Furosemide is a diuretic. Acetazolamide is a drug that is used for glaucoma. And therefore, you can have this group, you can have that group, the sulfonamide. The sulfonamide group is not specific for the sulfonamides. As we can see, it is also found in other drugs. Even the coxibs, we did find some of them do have the sulfonamide group, which was very, very important to give them rigidity and the ability for them to access the pocket which is within the COX enzyme. These are things that we have studied, so that they act as antimicrobial agents by inhibiting bacterial growth and activity, and are commonly known as sulfur drugs. So we are saying chemical modification of the sulfonamide structure has given rise to several important groups of drugs. The same point we have just said. So we do have other drugs. I have said acetazolamide used for glaucoma. Glaucoma is when you have high pressure in the eye. Diuretics like the thiazides, like furosemide, are diuretics, and mycobacterial agents like the sulfones, where we talked about dapsone, oral hypoglycemic agents, as we said in sulfonylurea. So we are only highlighting this point just to emphasize that the sulfonamide group is not selective for the sulfonamides or for antibacterial activity. It can be found in other drugs. The only thing that will differ is the structure, is how this group is arranged in the final molecule, and that therefore the structure of the sulfonamides for antibacterial activity will be completely different from the structure of acetazolamide, of the thiazides, of the sulfones, of the sulfonylureas. So here it is the structure of this drug that will give us the respective activity, whether it is diuretic activity, glaucoma, antimicrobacterial activity, and of course we will look at most of these compounds and you remember that point. So we are looking, when we look at the sulfonamides for antibacterial activity, we have just said you do have the SO2, and this is a sulfonamide group. That is a sulfonamide group or the sulfonamide group. And as you can see, this oxygen, we are saying double bond oxygen, and this sulfone group is directly attached to the benzene ring, and then at para position of that benzene ring, you also have another amino group. This group can be substituted, and even this amino group on this side can be substituted, and you see the need or the importance of the substitution. And of course, some of the substitution will lead to prodrugs, and of course prodrugs are inactive drugs. When they get into the body, they will have to be activated to the active drug. So you can have, so that group, you have sodium salt, water soluble. Of course, you can form sodium salt substitution on this group, gives different molecules having different pharmacokinetic properties. So we are going to look at the different substituents you can get at this position, and when the substituents you get at these positions are the ones which will determine actually even the name of the drug, what at this position. And you realize that one of the hydrogens can be substituted, but one hydrogen must remain intact. One hydrogen, with the exception of silver sulfadiazine, one hydrogen will always remain intact for purposes of ionization of the sulfonamide. This group can also be substituted, but if that happens, then the resultant molecule will be a prodrug. So we do require a free amino group for activity. If that group is substituted and in the body, it must be activated. It must be hydrolyzed. It must be hydrolyzed so that you get the free amino group, because it is only the free amino group that actually is responsible for activity. So these are some of the drugs that we were mentioning, and you can see like this is structure of furosemide. For now, you do not need to, you don't need to know the structure. It was just for purposes of us comparing these compounds. So that's furosemide, and you can see that is our sulfonilamide group there, or sulfonamide group there, and this acetazolamide. You can see that is our group there. So you can see in these ones, the group is free. The furosemide, the group is free. The acetazolamide, the sulfonamide group, the sulfonilamide group is free. Even in furosemide, we have dealt with the non-steroidal anti-inflammatories, the coxibs, and you can remember you have celecoxib, which again has a sulfonamide middle group there, which again is free. Then, of course, we also have valdecoxib. Those ones we just discussed them the other day. Then you can even see the hydrochlorothiazides. These are thiazide diuretics. Again, you can see that group is free. And then you can see these are the hypoglycemic agents, sulfonylureas. In the sulfonylureas, you can see similar to the sulfonamide, but this group is not an amino group. That group is not an amino group like in chlorpropamide. That group is a chloro group. So in the sulfonylureas, this R is not an amino group like in the sulfonamides. And you can also see, of course, there, and like in the other examples you have looked at here, the sulfonamide group is joined like in the sulfonamide, but you can see next to it is an acyl group. Next to it is an acyl group. So it's only that portion that is similar. It's only this portion there that is similar. The other portions are different. But all we want to show is that indeed the sulfonamide group is not unique for the sulfonamides. It can be found in other groups, but the other groups, the other compounds will have completely different structures. The structures will be such that they'll give the specific activity, and that's why we talk about structure activity relationship. So these particular structures will be related to their activity, just as we see for the sulfonamides. So they are effective chemotherapeutic agents used for the prevention and treatment of bacterial infections in humans. They are bacteriostatic. And when we come to look at their mode of action, they act by competitive inhibition. They do not bind irreversibly, as we found for the penicillins. Remember, penicillins bind the transport irreversibly, and therefore, more often than not, of course, therefore they are bactericidal. But these drugs will bind through competitive inhibition, so their activity is concentration dependent, and they have a wide spectrum of action. Their discovery is what we said was by chance. The discovery of prontosil antimicrobial effect in the early 30s of the 20th century represents the beginning of the chemotherapy development. So we are saying they were discovered by chance when using the prontosil dye. It was found that in patients who were given the prontosil dye, somehow if they had any wounds or if they had any infections, the infections were already cleared when they were given the prontosil dye. Remember, the prontosil dye was being given for another purpose, perhaps for investigational purposes. So when they were given the prontosil dye, they were found if they had any underlying infections that were cleared. So now they followed to find out what was happening to this dye, such that the patients who took it, if they had any underlying infection, the infection was cleared. And it was found the prontosil behaved like a prodrug. It was being cleaved in the body to give us a sulfonamide. So prontosil is an azo dye with a sulfonamide structure. In the human body, the prontosil is metabolized into sulfonilamide, and sulfonilamide was a prototype. Just 1 minute. Hello? Yes. Okay. Wĩcaitire nĩ wamĩmenya nĩ wathikwo mbere no wandũke ndikĩũĩ ingĩra ũkũũrie rĩrĩ Foreman Karanja ũria Karanja So we are seeing protosil is an azo dye with a sulfonamide structure. And as I have said, it's an azo dye. What we call an azo dye is that this compound that contains the N double bond N. It's an azo dye. And you can see what happened is that when it gets into the body, it is enzymatically cleaved. Enzymatically cleaved. When it is cleaved here, then this group here becomes an NH2, or this becomes an aniline and a sulfonamide. And that is what we call sulfonilamide. Sulfonilamide is the prototype. It was the first drug, or it is the first sulfonamide to be discovered. And this is a sulfonamide that acted as an antibacterial agent in those patients who were given prontosil. Of course, the other compound was 1,2,4-triaminobenzene. So you can see you can say position 1, 2, position 1, 2, 3, 4. Remember, we always say the lower these numbers, the better. Of course, you make sure that this number, the total, the addition of all these numbers is the lowest possible. So that's why we start from there. If we start from here, we see this will be 1, 2, 3, 4. That will be much higher. So you start from there, 1, 2, 3, 4, and that is 1, 2, 4, 1, 2, 3, 4, yeah, 1,2,4-triaminobenzene. So the prontosil dye was acted as a prodrug, and in the body it was enzymatically cleaved to give us the sulfonilamide. This is the same metabolic in vivo, and that gives us that, and the sulfonilamide. And this is the sulfonilamide that gave the antibacterial effect that was observed in those patients who were using the prontosil dye. Some of the things that we are talking about, presence of a free, for that prontosil red dye to have activity, it requires the presence of a free amino group for antibacterial activity. And that's why we are saying the prontosil, because it does not have a free amino group, it is a prodrug. In vitro, it is inactive. In vivo, it is activated. So that is our prontosil red dye. It has no free. It requires the presence of this free amino group. You see, this other one, not the sulfon. We're not talking about the sulfonilamide group. We are not talking about this group. We are talking about this other side, the aniline portion. The amino group must be a free amino group. If it is joined to any other group, then that drug will not have activity. And that's why we are saying that was a miracle that happened in those patients who are using the prontosil dye, and that is how they were found to have some healing effect, or they were found to improve from infections or even wounds, because the sulfonilamide did have activity. And then after this is the sulfonilamide, and all we are saying is that what we have already discussed, that group can be in many drugs, and these are the various drugs that can have the group. So we will not go back there. Now, these are just a few structures of sulfonamide medications. These are just a few of those drugs that have this group. We have said this group, the aniline moiety, must have a free amino group. You can see all of them. So you can see sulfamethoxazole. As I said, the name of this drug is not dependent on this portion, because all of them have that portion. All of them have that portion. The portion in these drugs that differs is the substitution on the sulfonilamide group. It is the substitution on this amino group that differs. Like if you look at this, this is an isoxazole, a methyl, actually it's a methyl isoxazole ring. So you can see that's an isoxazole ring, and this is the drug we call sulfamethoxazole. So that is sulfamethoxazole. You can see it has that, and it has the me is for methyl ring, and the oxazole is for this. But do remember, this is really not an oxazole as per se. It's an isoxazole, because when it's an oxazole, the oxygen should be on this side. It should be the nitrogen and the oxygen. So this nitrogen would be at this position. The nitrogen and oxygen are usually separated by one carbon atom for oxazole, but They prefer to call it sulfamethoxazole. Sulfamethoxazole, very, very important drug. It is even the drug that is being used in the management of HIV and AIDS. So sulfamethoxazole. This is sulfamerazine. So as I have said, the name, they are sulfonamides. So now for sulfamerazine again, you can see again SO2NH, one of the hydrogen there, substituted with a different group with retention of activity. And I want to believe this is the pyrimidine ring. That is a pyrimidine ring. So if you're seeing sulfamerazine and it has one methyl group at that position, sulfamethiazole, again, you see, it's not really thiazole. I don't know why they're naming them like that, because this is thiadiazole. You can see this ring is thiadiazole. It has 2 nitrogens, but this is what they call sulfur methiazole. Again, for it to be methiazole, there must be a methyl group somewhere. So that is sulfur methiazole. Again, sulfur moxo. Sulfur moxo, again, you can see what is differing is what is on this, or substitution on the sulfanilamide group. Sulfapyridine. This cannot be sulfapyridine. There is something wrong in that structure. For sulfapyridine, this should be a pyridine ring. That should be a pyridine ring. And a pyridine ring is a 6-membered ring with a nitrogen. So there is a small problem. Sulfoxazole. Sulfoxazole, you can see again oxygen nitrogen with 2 methyl group. Sulfamethazine. Again, the difference between sulfametazine and sulfamethazine is that sulfamethazine has 2 methyl groups as compared to sulfametazine, which has 1 group. So sulfamethazine, it is still a pyrimidine ring with 2 methyl substituents, both next to the nitrogen. So you can see how to remember it. Both are next to the nitrogen. With sulfametazine, it has only 1 methyl group. And we will see the difference. How do these 2 methyl groups, what's the difference in the characteristics of this drug, where you have 1 methyl group and in another one you have 2 methyl groups? Because there must be a reason why you have the 2 different drugs in the market. It is because they have different properties. So those are some of the drugs. So therefore, when we look at these drugs, there are very many, so I might not be able to cover all of them, but you can know the common ones. So this is what we are calling saying to be our general structure. Of course, here you can also have an NHR, but when you have an NHR, we are saying that drug is going to be a prodrug. It must be, and it must be hydrolyzed in the body to give us the active drug. So you can see R here for sulfadiazine, that's a pyrimidine ring for sulfadiazine. For sulfapyrazine, remember pyrazine as in pyrazinamide, pyrazine, the 2 nitrogens are para to each other. In the diazine, which has a pyrimidine ring, the 2 nitrogens are separated by 1 carbon atom. So that is sulfadiazine. That is a group that is at that position. Sulfapyrazine, that is a group at that position. Sulfadimethoxide, you can see it's still the pyridine ring, but it has the methoxy groups. Methoxy group. Sulfamethoxypyridazine, that is the group that we have. Again, pyridazine. The pyridazine ring is where the 2 nitrogens are next to each other. Sulfamethoxazole, we already looked at that. Sulfamethoxazole, a very, very, very important drug. Sulfadoxime, this is the one which was used a lot for treatment of malaria. This was fancied, used a lot for treatment of malaria. But again, as we have said, because of overuse and irrational use, there was development of a lot of resistance. The parasite, the protozoa, the malaria protozoa developed a lot of resistance. So now the use of the sulfadoxime was put to a halt so that we see whether they can't forget the resistance, or we can't forget, we can shed off the resistance and perhaps reintroduce the drugs much later. But I believe now the sulfonamides, not unless even areas where they have never been used, especially in Kenya, we are not using them for management of malaria because of the resistance. So these were drugs which could have been considered as water drugs. But of course, now quite a number of them are still being used. But as we have said, the major challenge is the fact that we do have a lot of resistance. So of course, again, this is just drawing some of them out. Sulfadiazine, we have said that is the diazine, sulfacetamide. For sulfacetamide, again, you have CO2, NH, and then one of the hydrogen is replaced by the acetyl group. This is what we call sulfacetamide. You can see one of the hydrogens is replaced by an acetyl group. This is mainly used as an eye drop. This again we have looked at. It's just again just trying to draw some of the structures out. Sulfur-pyridine, as I told you, the other structure had a small problem because this is the pyridine ring. So sulfur-pyridine, therefore, again, you can see the sulfur group, the SO2NH, and then you have the pyridine, sulfadiazine. Again, I hope that is a common drug, sulfadiazine, sulfamethoxazole. Again, we have looked at that. Again, the one of the hydrogens, that is the isoxazole ring. As I said, they call it methoxazole, but it has the isoxazole ring. So you have your own way of remembering. Have the isoxazole ring, and then it's methoxazole because of that methyl group. Sulfisoxazole. If you look at sulfisoxazole, very, very close structure to that of sulfamethoxazole. But you should note one difference. One of the major differences between sulfamethoxazole and sulfisoxazole, which will also have an influence on the reactivity, is that in sulfamethoxazole, the nitrogen is the one which is closest to the sulfonamide group. It is the nitrogen which is close. If you look at sulfisoxazole, it is the oxygen. The oxygen has a higher electronegativity than the nitrogen. So it will have a much more influence in pulling electrons to itself than the nitrogen. And of course, the sulfisoxazole has the two methyl groups, as opposed to sulfamethoxazole. But one of the major differences is the arrangement of the nitrogen and oxygen. In sulfisoxazole, the oxygen being much closer. Both of them are isoxazole rings, but in sulfisoxazole, the oxygen is the one which is closest to the sulfomoyl group, and in sulfamethoxazole, it is the nitrogen which is close. And as I have said, as we move on, we will be able to see that will have an influence on even the toxicity of these drugs because of the difference in the ability of this oxygen and that nitrogen to pull electrons. Then you have sulfasalazine. Sulfasalazine, as you can see here, SO2 there, and then again the nitrogen here again is an azo nitrogen. Here we have an azo group. Again, this sulfasalazine therefore is a prodrug, and this drug we will see mainly used for management of, I think it's called colitis, management of inflammatory bowel disease, because of this. If you cleave here, you will see, you will get, this is salicylic acid, amino salicylic acid. And amino salicylic acid, of course, has some anti-inflammatory activity. And of course, now this, when it is cleaved here, you can see it will give you sulfur-pyridine. You can look at it correctly. If you cleave it here, it will give us sulfur-pyridine, because that is a pyridine ring which is there, and you have cleaved it here, and this ring will be that one. So once you cleave sulfasalazine, it will give you sulfur-pyridine plus amino salicylic acid. Amino salicylic acid is important for bowel inflammatory disease, and of course, the sulfur-pyridine is an antibacterial agent and therefore can be important in case you do have an infection. But we will mention that in a short while. So those, I was just giving you some of the examples, and you need, of course, to learn some of those examples. As I have said, their names are quite related to their structure. There's a relationship between the name of the sulfonamide and with the structure. And of course, some of them will have one methyl group, some of them will have methoxy groups, some of them, the ring is different, some have a pyrimidine ring, others pyrazinamide, not pyrazinamide, but pyrazine ring, others have a pyridine ring, and therefore the ring is different, and that is also what makes this drugs different. So you need to know which ring is found in which of the sulfonamides. So that would be very quite of quite some importance.